Hello dear students, I am Surendra Jain, Master Teacher of Mathematics in Vedantu. In this session, I am discussing high weightage test 14, most incorrect questions done by the students. This test is based on relations, that is one very important topic for JEE mains as well as for JEE advanced also. So let's see what are those questions. So this question says, let a relation R be defined on the set of natural number n into n given by ordered pair AB related to ordered pair CD if and only if A power D is equal to C power B. Then we have to find whether this relation is reflexive, symmetric, or transitive, or equivalent, etc. Now let's start solving this question. So first of all, the condition given in the question is what we need to use extensively. Okay, so first I'll be checking whether this relation is reflexive or not. Reflexive means every element of n into n, that means that will be of the form a comma b should be related to a comma b. Now this is possible if and only if a raised to the power b, that is the condition here was that first element, if I call this as first, this as second, this as third, and this as fourth. Then first raised to the power fourth, so a raised to the power b should be equal to third raised to the power second. So a raised to the power b, which seems true. So this will be reflexive. So reflexive is correct. So reflexive is correct. Now coming to second, that is symmetric. Symmetric is if a comma b is related to c comma d, then we must have c comma d related to a comma b also. Now we will verify, we will check this using this condition only. This a comma b is related to c comma d if and only if, as per given in the question itself, a raised to the power d is equal to c raised to the power b. Now I can rearrange this given condition as c raised to the power b is equal to a power d, which is actually the condition as per this condition given in the question itself for c comma d related to a comma b, because this c raised to the power b will be a raised to the power d. So here you can see if this ab is related to c comma d is also related to a comma b, so we can say this will be symmetrical. Okay, now coming to transitive. So for transitive, we will be checking that AB related to CD and CD is related to, let's say, EF. Then we will check whether AB is related to EF or not. Now this if and only if, as per given in the question, A raised to the power D is equal to C raised to the power, I think C raised to the power B. Yeah. And for this, it will be E raised to the power, sorry, not B, it will be C raised to the power F is equal to E raised to the power D. Now, if I want AB related to EF, I will like to eliminate CD. And for that, what I can do, I will raise this first relation by power F and this by power B. So that this will be having C raised to the power B into F. This will also be having power C, power of C as B into F. So we can eliminate these two. So for that, what I'm going to do, I'll be writing this relation as A raised to the power D whole raised to the power F is equal to C raised to the power B whole raised to the power F. Similarly, here I will be writing C raised to the power F whole raised to the power B is equal to E raised to the power D whole raised to the power B. Now this C raised to the power F whole raised to the power B is nothing but C raised to the power F into B, and similarly here. So I can eliminate these two and we will be getting A raised to the power D into F is equal to E raised to the power D into B, which actually means, because in the power this number D is common, so you can remove this. So it will be A raised to the power F is equal to E raised to the power B, E raised to the power B. Now this means, let's write it here, this means A E is related to EF. Okay, A raised to the power F is equal to E power B. So A comma B is related to E comma F. That means it is transitive also. It is transitive also. Okay, so this is how this question is done. So it is reflexive also, it is symmetric also, it is transitive also. So this is actually equivalent relation. Let's see what are the options. The equivalent relation is one of the options, so that should be answer. Reflexive and symmetric but not transitive is wrong. Reflexive and transitive but not symmetric is wrong. And this is also wrong. So only correct option here is C. Now coming to next question. Now coming to this question, it says the number of relations on A which are symmetric and transitive but not reflexive. Dear students, this kind of questions you have to do by making few cases. Like if they are saying not reflexive. So not reflexive means your relation should not have 1 comma 1, 2 comma 2 and 3 comma 3 simultaneously. Because if these three ordered pair are there, it will become reflexive. So what I will do, I will make cases. Number one, that none of 1, 1, 2, 2, 3, 3 are there. None of 1, 1, 2, 2, 3, 3 are there. Let's see if this can give us symmetric and transitive or not. So dear students, in this case, if none of them are there, I think the first relation can be null set, where no element is there, but still we call that relation as symmetric and transitive. So one relation is this thing. Now coming to other relation, if I take let's say 1 comma 2, okay, then to make it symmetric, I have to take 2 comma 1. But if 2 comma 1 is there, 1 comma 2 is there, you will need 1 comma 1 and 2 comma 2 both in order this to be transitive. So this is not transitive. This can be symmetric, but this is not transitive. This means if I take none of 1, 1, 2, 2, 3, 3, I think there will be only one relation, that is null set. Okay, that is one case. Now 2. If I take one of 1, 1, 2, 2 and 3, 3. Out of these three, if I take only one of them, so let me take 1, 1 here. Okay, so if I take just 1, 1, I think this is symmetric as well as transitive, so this will be counted. Now, if I try to make one more relation from this scenario, when 1, 1 is there, okay, and I take, sorry, I take one more ordered pair, let's say 1 comma 2. For now to make it symmetric, I will have to take 2 comma 1 also. But to make it transitive, I will need 1, 1 and 2, 2 both. Same logic which I gave you here. So this seems that only with 1, 1 and not having 2, 2, we cannot have this relation to be transitive. So only 1, 1 or 2, 2 or 3, 3 type relations will be symmetric and transitive but not reflexive. So total number of relations will be 3 here. We got 1 here, 3 here, and then third case. Third case will be when 2 of 1, 1, 2, 2 and 3, 3 are there. Okay. If 2 of these 3 are there, what we can do? We will take 1, 1, 2, 2, okay, and that's it. This is also, symmetric, transitive, but not reflexive. But I think in this case, you will get one more scenario when you take 1, 1, 2, 2, and then you take 1, 2, and 2, 1. Okay, this is also transitive because 1, 1, 1, 2, 2, 1 requires 1, 1 which is there, 2, 1, 1, 2, so it requires 2, 2 for it to be transitive, so 2, 2 is also there. So this is also, transitive. So you can see here 3 relations of this type, because which two you are going to choose. So this kind of 3 relations will be there, and similarly this kind of 3 relations will be there. If you try to add one more ordered pair here like 1, 3, then you will need 3, 1 also, and for that you will need 3, 3 also. So this will not, this will become then reflexive, which we do not want. So total number of relations that it should be, number of relations with this condition, that is symmetric and transitive but not reflexive, are 1 plus 3 plus 3 plus 3. That will be equal to 10. Answer of this question should be D. Okay. So coming to the next question, In this question, we are given this question says number of relations on the set 1, 2, so that they are not transitive. Okay, we have to find transitive relations, sorry, not transitive relations from the set 1, 2. So here, the first case could be then you choose just one ordered pair. Actually, if you are going to write all possible ordered pair, when you take Cartesian product of these two elements, I think we will be having 4 elements here: 1, 1, 1, 2, 2, 1, and 2, 2. Okay, if I choose none, that is null set, but that is a transitive relation, so that we will be not counting. Okay, then if I choose one element, exactly one element, I think exactly one element, whatever you choose, I think this is going to be transitive, because with one ordered pair, you cannot check the condition of transitivity. So that means it will be transitive. Okay, then not transitive, I think we require at least two ordered pair, and these two ordered pairs should be of this type: 1, 2, and 2, 1, so that for this to be transitive, you will require 1, 1 also and 2, 2 also. So if I stop it here only, so that will be not transitive. Or if you take 1, 2, 2, 1, and then you take 1, 1 and stop, this will also be not transitive, because 2, 2 is also needed. And similarly, if you write 1, 2, 2, 1, and 2, 2, this will also be not transitive, because here we will be requiring 1, 1 also. So total number of not transitive relations on this has to be 3. So C will be the answer of this question. I'll just like to explain you this thing, that if you are having any one of the ordered pairs, maybe 1, 1 or 1, 2, okay, they will be called as transitive, because here condition of transitivity is cannot be checked, because only 1, 1 is there, other ordered pair is not there, so that I can check for third one. Same case here. Now in such cases, when you cannot check whether it is transitive or not, you will be saying it is transitive, because it is not violating the condition of transitivity. So we call them as transitive. So here answer should be C. Now coming to this question, it says two relations R1 on integer, one given by mod AB less than or equal to 2, R2 on non-zero real numbers, okay, defined by x R2y if and only if x equal to ky. That means y must divide x for some rational number k. Okay, not divide, actually it is not divide, it is just saying x equal to k times y. K is some rational number. Okay, now please see in this question this kind of relation. If I talk about R1 first, yeah, if I talk about R1 first, in this case you can see all a comma a will be related. A comma a will be related. Why a comma a will be related? Because their difference is actually equal to 0, which is less than or equal to 2. So this relation will be reflexive. Now this relation will also be symmetric, because if a comma b belongs to R1, then b comma a will also be belonging to R1, because difference will remain same. But dear students, when we are checking for transitivity, we can see some violation here, because if you choose two numbers, let's say 1 and 2.5, they are related, they are belonging to this relation R1, because difference is 1.5, and then 2.5 is related to 4, again difference is of 1.5, this also belong to R1. But you can see R1 comma 4 does not belong to R1, because difference will be 3. So this R1 is not transitive. So you can see R1 equivalent, that will be wrong. Both R1 equivalent will be wrong. Neither R1 nor R2 is equivalent. That we have to check by R2 now. Now to check this R2, what we will do, we will be first checking reflexivity. So for reflexivity of R2, I will need A related to A. That is, I think, possible, because you can say A equal to 1 into A. 1 is also rational number, and we are talking about these number A on non-zero real numbers. So definitely we can write this relation for all non-zero real numbers, A equal to 1 times A. So this is symmetric, this is reflexive. Now coming to symmetric. If A is related to B, and we have to check whether B is related to A or not. Okay. So for that, I think first of all we will be able to write that A equal to some K times B. Okay, but if A is equal to K times B, then we can definitely say B is also equal to 1 upon K times A. Now, K is the rational number, and K has to be non-zero rational number because A and B both are non-zero. So 1 upon K will also be non-zero rational number. So that means if A is equal to KB, then we can also write B equal to some K dash into A, where K is also rational number. So we can conclude that B will be related to A. So this relation is symmetric also. Now similarly, we can check if they are this R2 is satisfying condition of transitivity or not. So let's say A is related to B and B is related to C. Okay, this means A will be equal to some K1 times B and B will be equal to some K2 times C. Now combining these two relations, I can write A equal to, I think, K1 K2 into C. If you put B is equal to K2 C here, so we get A equal to K1 K2 C. If K1 and K2 individually are rational numbers, their product will also be rational number only. That means this, this relation for A comma C also satisfying this condition. So I can say A is related to C. That means this relation is transitive also. So R2 is all three. That means R2 is equivalent. So I'll go with only R2 is equivalent relation. This D is wrong. Okay. So this question is done. Now coming to this question, which says if R is having 3 ordered pairs on the set of A, which is having 1, 2, 3, the minimum number of ordered pairs to be added so that it becomes equivalent relation. Equivalent means reflexive, symmetric, and transitive. Now here, if we want it to be reflexive, already 1, 1 is there, so I will require to add 2, 2 and 3, 3. Here I am writing only those ordered pairs which should be there to make it equivalent. So this is needed to make it reflexive. Now 2, 1 is there, so I will need 1, 2 to make it symmetric. 3, 2 is there, so I will need 2, 3 to make it symmetric. Now you can also check, we want this to be transitive, and please see 3, 2 is there and 2, 1 is there. That means I will need 3, 1 also. I will need 3, 1 also, and then to make it symmetric, I will need 1, 3 also. Okay. And dear students, on the set of 1, if you do Cartesian product, there will be total 9 ordered pairs, out of which 3 are already given and 6 I have found here. That means in order this relation to make equivalent relation, you have to have the complete Cartesian product A into A, which we also call as universal relation. So here answer will be 6. That means 6 ordered pairs need to be added here. So answer for this will be 6. In this question, we are given R is smallest equivalent relation on the set 1, 2, 3, 4, 5, such that 1, 2, 2, 3, 4, 5 belongs to R. Then number of elements in R is. Dear students, I will like to tell you this question by 2 methods. One method I like to talk about equivalent class. Actually, there is a concept of equivalent class in equivalent relation where you can find few elements like 1, 2, 3, 4, 5 are there. So few elements creating class which are actually related to themselves only. They are not related to other elements class. Like here 1, 2, 2, 3 are looking like they are related to each other. So one class will be formed out of 1, 2, 3 elements. And other class will be formed using 4, 5. That means no 1, 2, 3 will be related to 4, 5 and no 4, 5 will be related to 1, 2, 3. So you make equivalent class of this, equivalent class of this, and if they both are satisfying this condition of equivalent relation, you will be able to know how many total ordered pairs are needed. So if 1, 2, 3, with 1, 2, 3, if I make equivalent class, so how much we will be needing? We will be needing 1, 1, we will be needing 2, 2, we will be needing 3, 3. Okay, but they have given 1, 2, 2, 3 also. So to make it symmetrical, I will need 2, 1, I will need 3, 2, I will need, that's it, 4, 5, I'll put it here. So let me just focus on this thing. So 1, 2 is there, 3, 2 is there. For 1, 2, I need 2, 1, and for 2, 3, I need 3, 2. But if 1, 2, 2, 3 is there, I will need 1, 3 also. And if 1, 3 is there, I will need 3, 1 also. So how many ordered pairs are required here? 1, 2, 3, 4, 5, 6, 7. 7 plus 2, 9. In fact, with 1, 2, 3, total number of ordered pairs could have been 9 only. So in fact, with the presence of 1, 2, and 2, 3, I think we need everything here. Okay, now with 4, 5, we will be needing 4, 4 and 5, 5. And because 4, 5 is there, I will be needing 5, 4 also. And I think that's it. Okay, with this 4, 5, I will need 3 extra ordered pairs, and then this will become total 4 ordered pairs with 4, 5, which will be equivalent relation, which will be satisfying the condition of equivalent relation within 4, 5. Okay, so that's the concept of equivalent class, where 1, 2, 3 elements are related with themselves, 4, 5 are related with themselves. So here they are asking, R is the smallest equivalent relation, then number of elements in R. So including these three, 1, 2, 3, and I think 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So total number of ordered pair would be 13 here. Actually, you can check, you can see one thing, that with 1, 2, 3, it is kind of equivalent relation and also universal relation. So total 9 elements are because of 1, 2, 3, and total 4 elements because of 4, 5. So 9 plus 4, 13 is the answer. Okay. Now, dear students, the second method of this question could be that if you do not know what is the concept of equivalent class, so what you will be doing, you will be just writing all required ordered pairs. So first of all, I will be going with 1, 1, 2, 2, 3, 3, 4, 4, and 5, 5. Okay, and then 1, 2 is there. Let me write 1, 2 also here. So I will need 2, 1 also. We are given 2, 3 here. So I will need 3, 2 also. Now because 1, 2 is there, 2, 3 is there, I will need 1, 3 also. And I will need 3, 1 also to make it symmetric. Okay, I think we can check for all the ordered pairs which are having either 1 or 2, the condition of transitivity is verified. Okay, and then we will see that 4, 5 is there. I will make 5, 4 also here. And for 5, 4, 4, 5, I will need 4, 4, 5, 5, which is already there. So this is what your minimum smallest equivalent relation will look like with these 3 ordered pairs. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. This is actually also same thing which we did in the method 1, but there we were having little bit of knowledge of some concept of equivalent class. So it was becoming more systematic, less chances of calculation error. But here we are doing same thing, but it is not considering that equivalent class of the class thing. And because we are asked actually that smallest equivalent relation is to be found, so we will not like to combine 1 with 4 or 1 with 5 or 2 with 4 or 2 with 5. So in a sense, we are actually doing the same thing that we did in method 1, but here without the concept, without knowledge of concept of equivalent class. Answer is same, that is C. Coming to this question which says S is non-empty set and PS be its power set. A relation R is defined on PS as R equal to A comma B. Okay, A comma B both belongs to power set of S, and PS is the power set of S. Okay, and A is subset of B. Okay, so R is defined on power set PS. Okay. So dear students, if A is subset of B, okay, so A comma A will definitely be lying in this relation because A is subset of A. But symmetric relation will not happen because if A is subset of B, you cannot say B is also subset of A. Why? Because if A is having less number of elements than B, then it doesn't imply B is also subset of A. So this will be reflexive, but this will not be symmetric. Now coming to transitivity. Dear students, if A is subset of B and B is subset of C, then I think from the knowledge of subsets, I think we can directly say there is no need to explain further. A will be subset of C. So that means if A is related to B, B is related to C, then A will also be related to C. So this will be transitive. So this will be transitive. This is not symmetric. This is reflexive. So symmetric, wrong. Reflexive and transitive, only correct. Reflexive and symmetric, wrong. Equivalent relation is also wrong. So answer for this is B. So that's it for this session. Thank you so much, students. Bye.